Have you ever seriously wondered what is really happening inside an AI when you ask it a question? Well, that's what we're going to do. We're going to go inside the machine and trace the exact journey your prompt takes, from the words you type all the way to the answer you get back. It really does feel like digital magic, doesn't it? You type in a question and poof, a well-thought-out answer just appears. But it's not magic. Today, we're pulling back the curtain to show you the elegant, step-by-step process that makes it all work. I'm sure you've seen this brilliant XKCD comic. It's hilarious because, it kind of feels true. But the reality of how a large language model thinks is actually this incredibly elegant process. It's a real engineering marvel, and it's all built on one revolutionary idea. And that big idea? It's called the transformer architecture. It came from this 2017 paper, Attention is All You Need. And it was a complete game changer. It moved us away from slow, one word at a time processing to something way, way more powerful. So for the rest of this explainer, we're going to follow a single prompt on its journey right through this exact system. Okay, so let's start the journey. Before an LLM can even begin to think, it has to read what you wrote. But here's the thing. It doesn't read words like you and I do. The very first step is to translate our human language into numbers, because that's the only language a machine really understands. Yeah, that's right. An LLM doesn't see words. It sees things called tokens. A token is just a small piece of text, and every unique token gets its own special number, its own ID. This whole process, tokenization, is the essential first bridge from our world of language to the model's world of math. Now, figuring out the best way to do this has been kind of an evolution. You could just split text by words. I mean, it's intuitive, but it breaks anytime it sees a word it hasn't been trained on. Okay, so what about splitting by individual characters? That never fails, but it creates sequences that are incredibly long and inefficient. And that's why the modern standard is subword tokenization. It's so clever, it breaks words into common parts, like token and isation. It really gives you the best of both worlds. It's flexible and it's efficient. But here's the catch. A token ID, like, say, the number 35478, is just a label. It has absolutely no built-in meaning. The model doesn't just need to know what the token is. It needs to understand what it means and how it relates to every other token in your prompt. And it does that with this brilliant two-part solution. First, something called an embedding gives the token meaning. You can think of it like a coordinate in a giant map of meaning. Words with similar meanings end up with similar coordinates. Then, a positional encoding vector gets added on top. This tells the model the token's exact position in the sequence. So now we've got both the what and the where. Now that our prompt has been translated into this sequence of information-rich vectors, it's ready to enter the engine room. This is the absolute core of the LLM, a stack of what are called transformer decoder blocks. I know, this diagram might look a little intimidating, but it's the actual blueprint from that original Attention is All You Need paper. For a generative model like the ones we use every day, we really only need to focus on the decoder section, right here on the right. Our vectors enter at the bottom and flow upwards through a whole stack of these identical blocks, sometimes a dozen, sometimes nearly 100, getting more and more refined with each step. And inside every single one of those blocks, the same thing happens over and over. You can think of it like a simple two-step dance. First, the tokens communicate with each other to build context, and then they compute, or think about what they've just learned from all that chatter. And this brings us to the absolute heart of the transformer, self-attention. This is the communicate step. Through a really clever system of queries, keys, and values, every token gets to look at every other token that came before it. Think of it like this. For each token, the query, it checks all the other tokens, the keys, to find and retrieve the most relevant information, the values. And by doing this with multiple attention heads at once, it can search for many different kinds of relationships all at the same time. After all that communication, it's time to compute. Each token's vector, which is now loaded with all this new contextual information from its neighbors, is passed through its own small neural network. This is where the model does the real heavy lifting, processing and refining its understanding before passing that result up to the next block in the stack. So the model has processed the prompt through all those layers. Now, how does it actually write a response? It doesn't write the whole thing at once. It does it one single token at a time in a loop. This is called the autoregressive loop. The model predicts just one token. Then that new token gets added to the end of the prompt. Then that new, longer prompt is fed back into the start of the whole process to predict the next token. It just regresses on itself, building long, coherent text step by step, piece by piece. To make that prediction, the model takes the final, fully processed vector for the very last token in the sequence. It projects that vector into a huge list of raw scores called logits, one score for every single token in its vocabulary. Then, a function called softmax turns all those messy scores into a clean probability distribution where all the values add up to 100%. And this is fascinating because everything we've seen so far, the tokenizing, the embedding, the attention, is completely deterministic. The same input will always produce the same list of probabilities, which means all the creativity or randomness you see in an AI's response comes down to this one final moment, how we actually pick a token from that list. And we have options. We can use greedy search and just pick the single most likely token every time, which is fast but can be very repetitive. Or we can introduce some controlled randomness through sampling methods like top K or the very popular top P, which create more diverse and human-like text by sampling from a pool of likely candidates. This is where the personality comes from. So we've completed the full journey of a prompt, from words to tokens to vectors, through the engine room, into probabilities, and back out to words again. But why is understanding this entire information flow, this architecture, so important for us as users? Well, it's because, as the AI community is realizing, it lets us move beyond just prompt engineering. We're shifting to something called flow engineering, where we can design these multi-step, interactive procedures that take advantage of the very architecture we just walked through. When you understand this autoregressive loop, this flow of information, you're no longer just talking to a black box. You can design better conversations, you can debug strange outputs, and you can build complex workflows that get far more powerful results from these incredible tools. It's not a magic box anymore, is it? It's a predictable, understandable system. Its architecture is an open book, and now that you've read it, the possibilities are entirely up to you. Thank you for watching.